Thank you everyone for joining us today for an overview and demo of the Cluster API and the Spectral Cloud Orchestration Engine. My name is Saad Malik, and I'm the CTO and co-founder here at Spectral Cloud. I'll be the host for the webinar. Joining me is Jun Zhao, who's the Chief Architect and Founding Engineer of Spectral Cloud. And before we begin, I do want to mention, feel free to post any questions you have either during the presentation and demo using the Zoom webinar's question section. We'll try to answer these questions as part of the presentation, and time permitting, we'll also host a live question and answer session towards the end. And now for the main event, Mr. Jun Zhao, over to you.
Thank you, Saad. Hello, everyone. Welcome to the webinar about the Cluster API and the Spectral Cloud Orchestration Engine. My name is Jun Zhao. I'm the Chief Architect here at Spectral Cloud. I was part of the Clicker team, so the previous startup co-founded by our CEO, Tenry. After Clicker was acquired by Cisco, I've built the Kubernetes management platform for Cisco Cloud Center Suite. And when Tenry, Saad, and Gautam started Spectral Cloud, I joined them from day one. So today we are going to talk about the challenges to manage Kubernetes clusters. And we'll look at one of the open source solution, Cluster API, which is built to make Kubernetes management easier, and how Spectral Cloud built on top of Cluster API to provide a better user experience with a live demo. We all know that Kubernetes makes life much easier to manage a containerized application workload. And with more and more enterprise running Kubernetes workloads in production, we see more challenges managing those Kubernetes clusters. And for many of the cases, Kubernetes is much more complex than the application running inside of it. So what are the challenges? We can look at the challenges at 3 different stages. First of all, we need to set up the infrastructure to run Kubernetes, like either in public cloud, private cloud, on-prem data centers, or edge locations. And each of these environments have very different setups in terms of networking and storage. And setup inside one environment is difficult. And you can imagine if you have multiple different environments to manage altogether. And once we have the infrastructure to actually bootstrap and configure the cluster, needs a lot of domain expertise. For example, do you want a cluster with a single master or HA? How do you want to manage the etcd cluster? Is it stack with control plane nodes or live outside of Kubernetes? And how to plan for the feeder domains to maximize your system availability? Also, for each of the components, like API server, controller manager, or kubelet, there are hundreds of configuration options. And Kubernetes API server has 148 options. And kubelet have even more, like 176. And you may also want to know what are the best practices for security. Do you want to enable audit log? How to set up the pod security policy? And also the questions need real Kubernetes expertise. And thirdly, once we have the cluster up running, there are still tons of additional integrations need to be configured to get a real production Kubernetes cluster, like CNI, storage class, authentication, logging, monitoring, security, etc. And once you finish all the integration setup, this is really just the beginning of the journey. Kubernetes has a new release every quarter, and together with the bug fixes and the security patches coming out like literally every week. So the day 2 management need continuous effort across all the 3 stages. And once more, this is just one Kubernetes cluster under management. And imagine if you need to manage tens or hundreds of clusters. So kubeadmin is the tool to solve the cluster configuration challenge. It simplifies the cluster bootstrap to literally just 2 commands. You do the kubeadmin init on the first control plane node and kubeadmin join on rest of the node. So kubeadmin internally will apply the default best practice for security, like auto-generated certificate, set up a mutual authentication across the component, and set up the basic RBAC model, etc. And Cluster API is another project aiming at the challenge of the infrastructure management, which is our main topic today. So what is the Cluster API? The main goal of Cluster API is to use Kubernetes to manage Kubernetes, using Kubernetes declarative API model, leveraging CRDs and custom controllers. The project started in early 2018 and currently in V1 Alpha 3 stage, with more than 200 contributors from companies like Google, VMware, Red Hat, Microsoft. And it has a long list of supported cloud providers, covers most of the public and private cloud environment, as well as bare metal. So how does the Cluster API work? It's built using custom resource definition, also known as CRD. So CRD is the way of extending Kubernetes declarative API model to manage pretty much everything. So CRD defines the desired state, then the custom controllers will just keep reconciling, trying to bring the resource to the desired end state. So if we take a Kubernetes cluster, add a CRD, the CRD will just include information like which cloud environment, or what is the Kubernetes version, how many master nodes, how many worker nodes. Then the customer controllers running inside a management cluster will just continue to trying to prepare the infrastructure, like set up the VPC, and also trying to launch a new node, bootstrap the node, and join the node to the cluster, and eventually bring up the Kubernetes cluster inside the target environment. So this works the same way how Kubernetes is managing pods and containers. The difference is instead of talking to Docker or Containerd to create a container, these custom controllers talking to the Cloud API, like EC2 or vSphere, to create virtual machines and other infrastructure like VPC or load balancer. So let's take a deeper look at the Cluster API CRD definitions. What are the CRDs needed to represent a running Kubernetes cluster? I think first of all, of course, we need a cluster CRD. And a cluster is composed of a group of nodes. So we need a CRD for the node as well. And actually, that's the two fundamental CRD the Cluster API has, the cluster and the machine. To make the system work across all the different cloud environment, Cluster API has additional cloud-specific CRD for both the cluster and the machine. For example, the AWS cluster contains information like which region, which VPC, and AWS machine contains information like instance type, AZ, subnet for each of the VM. Apart from the underlying infrastructure VM, we still need information to represent how to configure those VMs. And that is where kubeadmin config comes into picture. It'll generate user data, which contains kubeadmin bootstrapping command, then utilize cloud init to do the bootstrap when the VM is launched. So technically, with the cluster and the machine, plus the kubeadmin config, we are able to create a Kubernetes cluster. We just need to create one cluster resource and one machine resource for each of the nodes that you want to launch. But create a machine resource one by one is going to be difficult if you want to have like hundreds of nodes in the cluster. So to solve this problem, on top of the machine CRD, Cluster API also provided two higher level CRD to manage the control plane and workers separately. The kubeadmin control plane is used to manage the control plane node, handles functions like kubeadmin init, like etcd membership management, and upgrade and scaling of the control plane node. And the machine deployment is actually modeled after the pod and application deployment to provide the ability to bring up a pool of worker nodes with the exact same configuration. So let's take a look at one example about a cluster on AWS. So the first half are the resource that user need to define manually. You define the cluster resource together with the kubeadmin config template and AWS machine template for both the control plane and the workers. Then the controllers will just auto-generate the machine object from those template information. And once the machine joins the cluster successfully, it'll have a one-to-one mapping to the Kubernetes node object. This is a cluster on vSphere. For most of the parts, it's the same with AWS, with only two differences. The first one is the HA proxy load balancer. So this is used to set up HA inside of vSphere, because vSphere does not have a native load balancer service like Amazon ELB. To load balancer across multiple control plane nodes for the API server endpoint, vSphere Cloud Provider introduced this HA proxy load balancer, which will create a separate VM running outside of the Kubernetes cluster with the HA proxy running internally to send the traffic to all the control plane nodes. The second difference is the extra layer of abstraction between the vSphere machine and the vSphere VM. Actually, before the HA proxy load balancer was introduced, there was no vSphere VM. There's only vSphere machine, so it's the same model with AWS machine. So the main reason for the separation here is to reuse the code to manage the VM for both the HA proxy and the VM for the Kubernetes node. So we've talked about how to create a cluster, and now let's see how to do the upgrade. So there are two questions we want to ask for the upgrade. What needs to be upgraded, and how should we upgrade them? For the Kubernetes part, it will include all the Kubernetes binaries in the host, like kubeadmin, kubelet, kubectl. It will also include the container image for the control plane component, like API server, controller manager, scheduler, and all other dependencies like etcd or containerd, and of course together with some of the configuration changes. Another point we have to keep in mind is the underlying OS. For any OS level security patches, we need to keep the OS up to date as well. And how to upgrade them? Generally, we have two different solutions, either in place or replace. Oops, sorry, not this one. So in place means we keep all the Kubernetes nodes running, and we go to the host to upgrade the components and the binaries inside. So the host is mutable, and it will go through a lot of changes for all the upgrades. And this also means when you scale up to add a new node, those need to be configured with the same changes as well. And replace means we just kill the old node and launch a new node with all new binaries and dependencies inside. So this will keep the running host untouched and make it immutable. So the scaling will work perfectly without any special requirement. For now, Cluster API use replace for the upgrade. And I think this is the natural choice for cloud environment. because you can create and delete VMs quite easily. And actually, even for bare metal, the provider MetaCube is also using the Ironic to do the bare metal provisioning. So it followed the same pattern. But for other bare metal use cases like Intel notebooks, this might not work. Here are some of the main features in Cluster API roadmap. The version 0.3 was released in March, which added the kubeadmin control plane support, as well as machine health check for the worker node. Also, vSphere Cloud Provider added the support for HA in 0.3 release. Some other big features coming up are like machine health check for control plane node, the auto scaling support, spot instance support. The post-apply YAML experiment is to install the critical integrations like CNI or storage class, so that when Cluster API finishes the provision, you have a cluster ready to use. But this will only be YAML based and will not support other add-ons like monitoring or logging, which could be a Helm chart. So a quick summary for the Cluster API. It leverages Kubernetes declarative API model to manage Kubernetes cluster itself. It includes like cloud agnostic controllers to handle the common functions like kubeadmin, bootstrapping, and control plane and worker node management. It also have a cloud-specific controller to manage the actual cloud infrastructure, like a create and delete VMs. So with this, Cluster API can manage Kubernetes cluster on any environment. That's great. But is that all? Let's see what might be missing from this. First of all, OS. So the OS info input into Cluster API is a pre-built OS image. Cluster API release images for Ubuntu and CentOS for different cloud. But if you have any specific requirement, like if you want to use your own security hardened OS or install a specific library, then you have to build an image by yourself. And what does that mean is you have to repeat the work for all the upgrades, all the security patches for the day-to management. Because the Cluster API images need to pre-build the Kubernetes binaries, like kubeadmin, kubelet, and all the dependencies into the image. So I think this is one of the most difficult tasks. And what we really need is to manage OS and Kubernetes consistently within one system, one framework, rather than separately in different life cycles. Secondly, Cluster API only bootstrap the cluster using kubeadmin, and other integrations and add-ons like login monitoring will be managed separately. And especially when some of the integrations need specific settings inside either the host or the Kubernetes component configuration, that need joint effort across all the three system and life cycles. For example, if you want to enable authentication using DAX, then you will need to reconfigure the cluster with the correct API server configuration. So similarly, it makes sense to manage integration and Kubernetes under one system. And now I think the next question to ask is, what if we have a system to manage all the three pieces together under one lifecycle? And that is Spectral Cloud Orchestration Engine. The main goal of Spectral Cloud Orchestration Engine, what we call Palette, is to provide a single framework to manage operating system, Kubernetes, and integrations all together. It'll build on top of Cluster API to provide a simplified yet consistent user experience. The way we achieve this goal is to use a profile-based solution. We can logically separate Kubernetes into multiple layers, from OS to Kubernetes to CNI, storage, and other add-ons. Each layer can have multiple different implementation, which we call a pack. So for OS layer, we can have Ubuntu 18.04 pack or CentOS 7 pack. At network layer, we can have Calico, Flannel, and others. And then we pick and choose different packs to form a cluster profile. The cluster profile captures the static configuration of the full Kubernetes infrastructure stack. The padded orchestration engine will take all the pack definition and orchestrate the full lifecycle accordingly. Apart from the static information, we use a cloud config to represent the runtime cloud-specific configurations, like which cloud, which region, how many master, how many worker, and what are the instance types. So you can manage multiple Kubernetes clusters consistently from a single cluster profile. As we can see, the pack is really the building block for the system. So let's take a deep look at what a pack is. A pack is a collection of files with metadata definition as an implementation for a layer. And of all the different layers, we can roughly put the packs into 3 different types: the OS pack, Kubernetes pack, and other packs. A OS pack can contain information like a pre-built image ID. It can also contain a base OS together with the hardening script, so that for each of the new Kubernetes version, the padded system can automatically rebuild the image with the same base OS, the same hardening script, but different Kubernetes version. A Kubernetes pack contains, of course, the Kubernetes version, as well as additional kubeadmin configurations, like which plugin to enable, what is the audit log policy, etc. And other packs, including the CNI storage and other add-ons, will mainly contain either a manifest or Helm chart. So one thing here to notice is you can also specify any additional configuration needed for this pack, either inside the host or for the Kubernetes component. For example, for an OpenEBS pack, you may want to install the Escade service into the host. So if such information is configured, the padded system will customize the OS image to add the additional service on the fly. Another example, for an authentication pack like that, you can also specify the additional API server configuration like OIDC information. So the padded will add the configuration to the API server when bootstrap the cluster. So internally, padded contains 3 components: the image manager, cluster deployer, and integration manager. Image manager will first prepare the OS image, so either import a pre-built image or build the image on the fly. So with the host configuration requirement from all the different packs, not just the OS pack. When OS image is ready, cluster deployer will talk to cluster API to create and bootstrap the cluster. Again, with all the Kubernetes configuration from all the packs, not just the Kubernetes pack. Once the cluster is up, the integration manager will go ahead and set up and configure all the integration points and the add-ons. So the day 2 maintenance, like scaling upgrade, will be managed by the same controller in the same way. So with that, let's see a demo. For this demo, we'll use a current cluster on my laptop as the management cluster. From there, we'll create a HA cluster inside of VMware. So for those of you who don't know about Kind, it's called Kubernetes in Docker. It's a developer tool to create a Kubernetes cluster using Docker to make it easy for dev testing. After the first control plane node is ready, the padded inside the management cluster will pivot and transfer the control to the target cluster. Then the management cluster is actually not needed after that. And from the target cluster, it will try to scale up the remaining control plane node creating all the workers and install the add-ons. Then we can do the upgrade directly from there. So with that, let's dive into the demo. Let me share my screen with demo. Okay, so to save us a little bit of time, I already have a Kine cluster running in my laptop, and I have installed the padded controller inside the Kine cluster. To create the actual target cluster inside of VMware, what we need is only 3 manifests: the cloud account, the cluster definition, together with the cloud config. So let's kick it off, and we'll go ahead and look what's inside each of them. The Spectral Cluster CRD contains the main information is the cluster profile. And in this cluster profile, we have defined the 6 packs with a Ubuntu 18.04 as the OS. Again, to save us a little bit of time, I'm using a pre-built Ubuntu image ID for the Kubernetes node together with the load balancer node. For the Kubernetes layer, we're using 1.7.3 together with the Calico and the vSphere storage class. There are also 2 add-on packs, the MetaLB for the load balancer and the Prometheus for the monitoring. So for all the packs that we define within the cluster profile, it's actually a reference to the actual pack hosted within the pack server. And we are using the smart tagging for the reference. So you can specify the exact version of the pack, like the Kubernetes. You can also using webchar to match for the latest version. So whenever there is a new pack version available, the padded system can do the auto upgrade based on your maintenance policy. Within the cluster profile, we can refer to the pack from multiple different pack servers. Spectral Cloud will have 1 public pack server with all of our out-of-box content that we provide. You can also host your own pack server with the packs developed specifically for your own environment. All the packs within the pack server have their own definitions with their own default configuration. And we can override those default values from the cluster profile. For example, for the MetaLB, I am providing this specific static IP pool for this cluster only. Other than the cluster profile, the Spectral cluster also contains the reference to an actual vSphere cloud config. So let's take a look at what the cloud config is. The cloud config contains, first of all, the reference to a cloud account. So the cloud account contains information like your username and password for your vCenter, and this will be stored inside a Kubernetes secret. Other than that, the cloud config will contain the cluster level configuration. So for VMware, it will be placement properties like data center, data store, networking. And then it will contain an array of machine pool. So here we have 3 machine pool defined, 1 master machine pool with 3 nodes defined, and 2 worker pools with 1 node each. With the machine pools, you can use like different infrastructure configuration for your cluster, like different CPU, different memory, or with GPU support. So these are all the information that is needed to create a Kubernetes cluster. Let's check what is going on right now in my Kine cluster. As you can see, the Kine cluster, the padded controller have automatically installed the cluster API controller for the VMware. And we can see right now there should be 1 control plane VM is under provisioning state. So this provisioning will take a little bit longer, like 10 to 15 minutes. I have another cluster launched previously, so we can take a look at what's inside. Here, this cluster is launched using the same cluster definition and the Cloud Compute definition. We have 3 control plane nodes running and with 2 workers. If we check the machine object, we can see there is a one-to-one mapping from the machine to the node, 3 control plane machine and 2 workers. And if we check the kubeadmin control plane, you can see there are 3 replicas. And the main information defined within the kubeadmin control plane is this kubeadmin config spec. So actually, all these configurations come from the Kubernetes path that we define, and it will include all the security best practice from the CIS benchmark. And also, you can see it contains the replica information. Right now, we have 3 replica already. For the worker node, we are going to have 1 machine deployment per worker. And you can see the machine deployment will contain the reference to the actual template information that is defined. If we check the vSphere machine, you can see for each of the vSphere machine, it will include information like the actual CPU memory and what is the image ID that is used to launch this VM. So this is another one we can check is the vSphere VM. The vSphere VM, here we can see the load balancer. So the load balancer node will not be part of the Kubernetes node, but here you can see the load balancer node is also managed altogether. Let's take a look at all the add-ons that we have defined for the MetaLB and the Prometheus add-ons. It's all installed correctly. And if we check the load balancer service, you have the actual load balancer service that for the Grafana dashboard. So we can log into the Grafana dashboard to check what is actually going on. So this is how the running cluster of a cluster API created inside VMware. If we check the pod, what is currently running, we can see the pallet controller right now is running within this system. So this pallet is kind of in control of the system itself. And now the creation part we have seen, we can directly try an upgrade. The upgrade, to trigger the upgrade, is actually quite easy. We can check. What we need to do is just change this Kubernetes version. And since we are using a pre-built image, we want to change the pre-built image as well. So let's go ahead and change the version to trigger upgrade to see what is going on. Let's see, we wanted to upgrade from 1.17 to 1.18. We have the 2 pre-built image already within the vCenter. So let's just save this change to trigger the upgrade to see what is going on. After we change this, we can take a look at the kubeadmin control plane. So now you can see the replica of the kubeadmin control plane is 4, with the 3 replicas ready and 1 is unavailable. If we check the machine object right now, you can see there is 1 control plane machine is under provision. And if we check the vSphere machine, this one just got launched. So the upgrade will actually take a little bit of time. We can see the machine will take some time for the new actual VM to come up, to finish all the cloud init bootstrapping. And then the cluster API, the controller, will try to bring up all the nodes one by one. First, upgrade all the control plane, and then upgrade the worker machines also one by one. So with that, I think that is pretty much for the demo. Let me switch back to the slide. With that, I think I will hand over to Saad to talk about the Spectral Cloud as a whole architecture. Saad, please.
Yeah, thank you so much, Yoon, for that awesome presentation and demo. And just before we open it up for questions, we'll cover one more slide in terms of how the Cluster API and the higher level Palette Orchestrator fits into the Spectral Cloud platform. So as Yoon already mentioned in the presentation, what we've seen is despite the excitement around Kubernetes, many organizations are finding it challenging to operate and run Kubernetes in production. Kubernetes is an open source project, and to make it production ready, you really need to integrate multiple different integrations, sometimes almost 24. Now, on top of that, Kubernetes itself has various integrations that are very fast release cycles. So security releases are coming out every week or so, and new releases are coming out maybe on a quarterly basis. Upgrade, maintenance, and performing all these day two operations require constant effort. And as you can imagine, all of this is significant effort for even a single cluster, but it becomes exponentially more difficult when dealing with multiple clusters. And sometimes these clusters are even across multiple environments. So how do we provide a real solution and keep it consistent in all these factors? This is where Spectral Cloud comes in. It is a multi-tenant SaaS platform, which gives enterprises control over the Kubernetes infrastructure stacks consistently and at scale. It helps to think about what we built in two parts. The first part is what we think of as modern table stakes Kubernetes management, giving tenants the capability to provision and manage Kubernetes clusters across public and private clouds like Amazon, Azure, VMware, and also bare metal. And we provide a managed Kubernetes-like experience for these clusters, including full Kubernetes lifecycle management, continuous upgrades behind the scenes, and also provide typical enterprise features such as single sign-on, RBAC, quota control, and much more. So our unique angle is on the right-hand side, where we provide profile-based management of the Kubernetes infrastructure integrations. The idea here is to give organizations control through flexibility. So users go through and they define these cluster profiles, which June described, which is customized for their own integrations and requirements based on what's needed for their organization. Cluster profiles can be different from group to group without having to deal with the complexity and scalability of a do-it-yourself project. And as June covered in the presentation, the cluster lifecycle management is done in the context of the entire infrastructure stack. This includes everything from the operating system, Kubernetes, storage, networking, and many, many additional layers. Some of the additional layers that Spectral Cloud provides supports for include monitoring, logging, security, load balancer, authentications, and more. Out of the box, we provide many different integrations and implementations, but we also make it really easy for users and customers to add their own integration packs as needed. If there are any updates that are triggered on these cluster profiles, all the clusters using that profile would be updated to the latest version. The updates themselves can be triggered either via our portal or in our UI, or via our published open APIs. We can also automate the update of these clusters by attaching a maintenance policy which governs when and how the updates are propagated to the clusters. So essentially, these maintenance policies dictate timing and manner. For example, which days of the week should the updates go through, and the canary or blue-green strategy. So there's obviously a lot more to the platform, which we'll be happy to discuss with you. But for now, maybe we can open up for questions for Cluster API, for Palette, or in general, any questions you may have about Spectral Cloud. And as of right now, no questions. You guys, please feel free to ask questions. Maybe June, I can start off with a question, easy one for you. How do you, if you think about the node health, if something goes wrong to a worker node, what does Cluster API and what does Palette do to reconcile and fix the node?
Well, when the node goes wrong, there are really many different reasons which a node can go wrong. For example, when the node through the bootstrapping, the cloud init could go wrong, when the node try to do the kubeadmin join, maybe there is some networking issue, it cannot join the cluster. Even if when the node successfully join, later on, there might be some other issues, might be some application running inside, or the node is under very heavy load, so it become unready. So of all the different reasons a node could go wrong, the machine health check is really aiming to solve most of them, if not all of them, together. So the machine health check will try to periodically check whether the node is ready or not. If anything goes wrong, like the cluster PI does for the upgrade and scaling, it would just try to launch a new node. It's not trying to fix the current node because it might be many different reasons. It was just trying to launch a new node because with all the immutable OS and the whole upgrade system, it was just trying to launch a new one and kill the old one. So maybe the underlying issue might be still exist. So, but for most of the case, if the node specifically, not the underlying infrastructure, it will try to launch a new one, and hopefully that issue will be gone. Yeah.
Awesome, thank you. Guys, feel free to raise your hand if you have any questions. Okay, and June, so the other functionality you mentioned is coming in the next version of Cluster API. Can you talk more about the custom load balancer support that they're bringing in?
Yeah, the cluster load balancer right now, as we have seen, the VMware have this HE proxy load balancer, but it is done inside of the VMware cloud provider itself. It's not done at the whole framework level. Actually, apart from VMware, there might be other provider which need the same load balancer service as well, like the MetaCube for the bare metal support. So for the next coming release, the Cluster API plan to bring the load balancer support at the framework level. So that support will be available for all the cloud if you want to use.
Awesome, very cool. Cool, guys. That wraps up the Cluster API and Spectre orchestration webinar. Thank you so much for joining the webinar, and please do check out our website, spectrecloud.com, if you have any additional questions. Our contact information is available on the website. Thank you again, and have a wonderful day.
Thank you, guys.
Thanks. Bye.